Hey, welcome back to the second part of this lecture on efficient linear reconstruction attacks. So in the last video, we talked about a query-efficient reconstruction attack that can reconstruct given a database of size n, given order n random queries on that data set, provided they're answered with sufficiently small noise. But I want to talk about two more issues related to this attack. So the first one is I'm just going to explain what goes into making this attack run in polynomial time at a very high level. And then I'm also going to talk a little bit about kind of what it looks like to try to actually use this attack in practice. And I will talk about an example of an actual system that has actually been broken using this attack and tell you a little bit about how it was done. So to start, let's talk about making the attack polynomial time. So what was the reconstruction attack itself? So it took in as input a vector of k queries, or sorry, a set of k queries, each one is a vector, and a set of k answers to those queries, each one is a number. And it tried to find some s tilde that minimized the quantity, which is represented here, where the quantity is the largest over all the queries of the error that the answer would have if s tilde were the true vector of bits. All right, and computing this quantity can be done efficiently, right? So if I give you some s tilde, you can compute this in time proportional to roughly k times n, which is it takes about order n time to evaluate a query, and you have to do it k times. So it takes about order nk time. But the problem, right, is that searching over all of this takes order 2 to the n, or in fact exactly 2 to the n vectors to try. All right, and it's not really possible to make this attack kind of as stated efficient if you insist on this integer version of the attack where we're trying to find a binary vector 0, 1 to the n. So, but what we can do is we can use a tool called linear programming and relax the problem a bit. So linear programming is a rich subject. You could teach an entire course on linear programming. But let me give you just the basic gist of what a linear program is. So a linear program essentially asks you to optimize some linear function of a vector x subject to some linear constraints. So what does that mean? So it means that I want to maximize some linear objective, which is specified by saying maximize over all x of c dot x. Okay, so I want to maximize this linear objective. And subject to the constraint that for a whole bunch of vectors v and numbers b, vi dot x is at most bi. All right, so there's first of all, I should say there's a lot of ways to write linear programs. There's lots of like equivalent formulations with maximums and minimums and inequalities and equalities and other things like that. But the gist is that I want to maximize some linear function. So I want to like push x really far in some direction, subject to a bunch of linear constraints. So barriers that say, do not pass this line, do not pass this line. Okay, so linear programs are a really important tool in optimization and computer science. They come up everywhere. If you have a chance to study them in more detail, I recommend it. But all I want to tell you is that if I give you a linear program in this form, you can solve it in polynomial time in the number of variables. So order the number of variables and the number of constraints, which is order, so order n times m to some constant. It's a little more complicated because the constraints and the objective are actually real numbers, so we have to be a little careful to specify how they're given to us and how complex the real numbers are. But for purposes of this course, just assume you can solve this in polynomial time. And perhaps more importantly is this is very efficient in practice. So not only are there polynomial time algorithms for solving linear programming, but in fact, there are just practical algorithms that eat these up. So now, of course, the thing I wrote above doesn't look like a linear program. It takes a little work to massage it. So I'm not going to tell you exactly how to massage it into a linear program, but it's like a good exercise to try sometime. What I'm going to do is just highlight the most important thing, which is that we're going to replace this with find S hat that is a real valued vector with entries in 0 to 1 to minimize the same quantity. All right, so we're going to now search for this vector S hat, and doing that is going to be essential to make it a linear program. And then we're going to round S hat to S tilde. Okay, so we're going to use the linear program to find a real valued vector S hat, but that's not a reconstruction. That doesn't tell us secret bits. It tells us secret numbers. But we can round it to a Boolean vector. And so there's a little bit more work when you have to analyze the linear programming version of the reconstruction attack. The first is you have to analyze the rounding. So you have to relate the kind of the reconstruction error of the S hat to the reconstruction error of S tilde. So there's a little work to do there. And the other thing that you have to do is suddenly when we talk about eliminating vectors S hat, well, there's an infinite number of vectors S hat. So we have to change our proof strategy just a little bit. But the bottom line is that the theorem I gave you is still true for this reconstruction attack. So the theorem about the 0-1 valued reconstruction attack that's not efficient, it's still true for this attack. It just takes a little bit more work to show. But you can feel free to just trust me on this one. Okay, so the bottom line is that we can express the optimization problem in this reconstruction attack as a linear program and solve it polynomial time in the worst case and also very efficiently in practice. So the sort of more, this is why we kind of emphasized the inefficient reconstruction attack first, because the sort of more interesting part of the attack is actually the understanding how the number of queries and the reconstruction error relate. So okay, that's all I want to say about making it efficient, but the bottom line is that we can do efficient reconstruction. So computational costs are not actually a barrier to doing reconstruction in practice. So now let me talk a little bit about how you're going to use this. And I'm specifically going to talk about how these ideas have been used to attack an actual product called Diffix, which is a system for private analytics made by a product called AirCloak, made by a company called AirCloak. And in particular, AirCloak has released something called the Diffix challenge, where they will pay you money to break their system to find vulnerabilities of exactly the kind that reconstruction attacks are meant to exploit. And I'm going to describe just a taste of what went in to an actual attack that claimed one of these prizes. And subsequently, the system was patched, and another group claimed that prize. And so if you're looking for a fun and possibly lucrative course project, maybe look up the Diffix challenge. But let me explain what Diffix is trying to do. So Diffix is like an SQL-like system, a SQL-like system that lets you ask queries of the form I wrote here. So select, if you don't know SQL, what this is basically saying is look at the table loans. So there's some table called loans, and count everybody who has a loan status of C. I don't really know what C means, but loan status of C, and who has a client ID between 2000 and 3000. So what does that kind of look like in our language? Well, you have a data set called loans, and in this data set, let me make it. So in this data set, what do you have? You have a client ID and a loan status. And first of all, to make it match a little better, I'm just going to treat the loan status as 1 or 0. But of course, you can map C to 1 or 0. So your client IDs, there's a whole bunch of them, 2000, 2001, 2002, up to 3000. There's obviously more. There might be more in this data set. And the loan status is 0, 1, 1, 1. Okay, so this is like your table. And notice that this fits very well with our model for reconstruction attacks. This is some kind of identifier, and this is a secret bit. Okay, so the kind of queries that we're asking say, first of all, let's ignore everybody in this table whose client ID is not between 2000 and 3000. So we can just think of this as a table of size 1000. Okay, so we have a table with n equals 1000, and everybody has a public identifier. That's some number between 2000 and 3000. So very clean setup. The identifier is literally just a unique number. And everybody has a secret bit that's 0 or 1 indicating their loan status. So this is exactly the kind of table that we have studied. And what the reconstruction attack says is that if I can issue queries that ask for different subsets of these client IDs between 2000 and 3000 and return the number of the number of people in them that with loan status 1, then I should be able to reconstruct the loan status. Okay, so count queries. This is a count query as we defined it. It says sum over like ID equals 2000 to 3000 of 3000 of loan status for client ID for that person's client ID. I'll write it as like. Okay, and so what we'd like to do is we'd like to ask queries of the form sum over all these people, some fee of client ID times loan status ID. We said that if we can do that, then we can reconstruct the IDs. Okay, so we just need to specify these fees that tell us which client IDs to select, and then we can, we'll try to choose them at random. Okay, so what does so like this interface should be rich enough to reconstruct. So what does, what would it look like to ask random queries? Well, a random query, you could do, select count from loans where, interestingly, this is the first time in my life I've tried to write out a SQL query by hand. Loan status equals 1, and client ID in 2000 to 3000. And here's where it's interesting. So we also want and ID equals, let's say, 2001, or ID equals 2002, or ID equals 2007, ... And we just include exactly the client IDs we want. So we're going to randomly pick whether to include each client ID, and that's going to give us some query that just tells us about 500 client IDs we want to include at random, 500 give or take. Right? So we're just going to pick at random whether we want to include that client ID in the query, and for everyone we do want to include in the query, we will add an extra clause to this SQL, to this last part. Okay, so we're looking for everyone just within 2000 to 3000 because we don't want n to be too huge, and we're looking for this random subset. Now, Diffix, like the makers of Diffix, were not unaware of reconstruction attacks. So what they thought is, I need some way to ensure that if somebody tries to run this type of attack, the noise we add will be proportional to root n. Because, as we said, the reconstruction attack with this many queries will actually fail if the reconstruction is not proportional to root n. So there's a lot of ideas that went into Diffix to sort of try to prevent attacks. But one in particular is the idea that sort of they should make sure that if someone tries to ask like random queries, the noise will be kind of proportional to root n. And so what they did was they basically said, oops, let's see if I can get just the right spot. So what they did was they basically said, let's add noise proportional to the kind of length of the query. So there's sort of two steps. So one is they add noise kind of proportional to the number of users that are like possibly relevant for the query. So because you're asking about client IDs between 2000 and 3000, everything is now, it's as if the database sort of went away. So n is now 1000. So they kind of want to set it up so you add noise proportional to like the size of the part of the data set you're kind of zooming in on. But the important part is that they add noise proportional to the like syntactic length of the query. And since this query is going to have about n over 2 clauses, what that means is that kind of random queries get noise about square root n. Okay, so a random query on a set of n people will get noise about square root n. Okay, so if I tried, so it's proportional kind of the number of people I'm trying to ask a random query about. Okay, so it kind of looks like they've taken care of this. If I really try to run the attack exactly this way, the noise will be enough to prevent reconstruction. So what's the problem? The problem is that specifying really random queries is going to require a query that is kind of syntactically very complicated. It's going to have like this and of ors where there's many, many terms in the ors. But maybe we don't really need random queries. Maybe what we can do is something that is kind of random enough, but is syntactically kind of simple to make. So if you're familiar with things like hashing, maybe what we should do is not actually choose a random hash function, but some kind of weakly random hash function. If you're familiar with this theory of pseudo-randomness, we'd like to choose some set of queries that are kind of not truly random, but are sort of random-like. There's what's called pseudo-random in particular notion. And how you do this is a little complicated, but a sort of clever attack by Kobe Nissim and Aloni Cohen in 2018 came up with this funky looking set of queries that turn out to basically be random enough. And the key part of the query is to do this sort of weird operation on the client ID. So where this operation comes from is a little tricky to describe, but the gist of it is that it's attempting to select a subset of client IDs that's kind of messy enough. It's not, it's sort of random-ish. It has kind of the right properties of random queries. And it sort of turns out after some experimentation that this is a good way to do it, basically. So what happened? They came up with these queries. They look very funky, but there's some intuition behind them. It's not like a completely nonsensical thing to do. They used these random queries, which notice are very syntactically simple. They only have a small number of terms in the query. So the noise added was not proportional to square root n. It was very small noise. And they were able to reconstruct the lone status basically with perfect accuracy, almost perfect accuracy. So they claimed the Diffix challenge, and Diffix responded by basically making it not allowed to, they added sort of syntactic rules that eliminated this type of query. And in particular, they basically said you're not allowed to do funny math on the client IDs because the client IDs are unique. So you're only allowed to do funny math on columns that are kind of have, don't have too many unique entries. But another attack came along and figured out how to combine lots of columns that are not unique into sort of, sort of overall to produce kind of a set of unique IDs. And this process, is, I think that's roughly where we are now. So they've issued a patch, but it's unclear to me that there's like an end game here. So I think the point is that even though the theory of reconstruction gives you these nice clean theorems that are a little bit specialized, like if you ask random queries, you get reconstruction with this error, the bottom line is that any sufficiently rich set of queries is likely to let you do reconstruction. And I think that's a pretty robust phenomenon. So that wraps up the 2 lectures on reconstruction. So the key points I want to recap from just this video are that we saw a theorem that says you can reconstruct a data set of size n with n secret bits using a linear number of random queries, provided the error is less than square root n. So the informal version of this says that if you're going to let a user, if you're going to try to release about n statistics that are sufficiently kind of rich on a data set of size n, and you want to avoid reconstruction, then you need to add a significant amount of noise. Okay, and we also show that this can be done in polynomial time, or I sketched that it can be done in polynomial time. And the important sort of take home is that even though this theorem applies to random queries, in practice it's very difficult to constrain the queries enough to prevent reconstruction. So lots of types of queries allow reconstruction. There's a very beautiful theory of which types of queries allow reconstruction, but also I think just in practice it's worth assuming that reconstruction can be performed kind of unless you know otherwise. So that's it for reconstruction. Adam's going to do the next lectures introducing the basics of differential privacy, which is a remedy for reconstruction attacks and a host of other attacks. And I will see you in class. Thanks.